Hi folks, so this is the last muscle lecture right here. So we're going to go back to fast twitch and slow twitch fibers briefly, but from another angle than just looking at the speed of the twitch. So first of all, slow twitch fibers have another name. They're called red fibers, and that's what this R stands for right here. R for red. And fast twitch fibers have another name. They're called white fibers, and they really are white. Fast twitch fibers really are a lot paler than slow twitch fibers. And the reason for this is the amount of myoglobin and mitochondria in the fibers. Mitochondria, by the way, has some respiratory pigments in its membrane, so you would have some color from the mitochondria, as well as the myoglobin, which is red like hemoglobin. So the slow twitch fibers has a lot of myoglobin, and that's why they're red, and the fast twitch fibers has very little myoglobin, and that's why it's paler or white, what we say. You can see the twitches again. You can see the soleus muscle, for example, is a slow twitch fiber, whereas the gastrocnemius and the lateral rectus muscle of the eye, and other eye muscles, by the way, are fast twitch fibers. And another thing I want to add to this is this. We just talked about how these slow twitch are high in myoglobin, so that's why they're red, and the fast twitch are low in myoglobin, and that's why they're white. But in addition, the slow twitch fibers are high endurance, low power. High endurance, low power. Whereas the slow twitch fibers are low endurance, they fatigue easily, but they're high power. So you can that's another big difference between fast twitch and slow twitch fibers is the power and the endurance. All right. So who do we recruit when we're performing an activity? Because remember, let me remind you that with any given muscle organ, for example, this biceps brachii right here, when you do a movement like a curl, like whether you're curling a dumbbell or an ice cream cone, it doesn't really matter. When you do a movement, you're recruiting motor units. Remember, one motor neuron innervates X number of myofibers, and they're all or none, so that's one motor unit. Well, the answer is you recruit the fibers which do the job you need to be done. For example, if you have a small load, you're going to recruit a whole bunch of high contractile duration fibers, endurance fibers. And you're not going to recruit hardly any of these high velocity fibers. I mean, do you really have to lift the ice cream cone to your lips as fast as you can go? And no, and in fact you probably wouldn't because you'd smash your ice cream in your face. So you wouldn't recruit that many fast twitch fibers. You would recruit more slow twitch fibers. And now here's the thing though. With any given motor unit, you might actually have a mixture of those fibers. But if you look at the whole organ, say like the gastrocnemius, it's predominantly fast twitch fibers, and the soleus is predominantly slow twitch fibers. So if I'm going to go for a long walk, I'm going to use a lot of my soleus muscle. But if I'm going to play a game of basketball and have to sprint and jump constantly at maximum power, I'm going to use my gastrocnemius. So you can see that we do divvy up our jobs. Our muscles are recruited based on what we need at the time. And this would be a slow twitch endurance fiber right here. And this would be a fast twitch power fiber right here. This is comparing the fibers. You can see that the fast fibers. Now let me just tell you something. These are your typical fast twitch fibers that I've talked about before, but they actually have a name, and that's 2B, or a number, that's 2B. Whereas slow twitch fibers are Roman numeral number 1. Fast twitch fibers, these are the highest power there is, but they are fatigable. They have low endurance. Now, as it turns out, there actually is another type of fast twitch fiber, and it's called 2A. And it is fast twitch. It does have power. And it is fatigable, but it's a little bit resistant to fatigue. So does it have the endurance of slow twitch? Absolutely not. but it's resistant to fatigue, which means it doesn't fatigue as fast as the 2B. That's what it means. And these are fast twitch 2As. Now let's go down through here. Notice that the cross-sectional diameter of fast twitch fibers are large. So these are big muscles. This is why when bodybuilders do workouts to win a competition, they're not building their slow twitch fibers. They're building their fast twitch fibers because their fast twitch fibers have large cross-sectional diameters. These are the bigger muscles. Of course, they're rapid time to peak tension because they're fast twitch. Let me see. Color, white, or very pale anyway. Okay. Why? Myoglobin is low. Alright. In addition, look at the capillary supply. Scarce capillary supply. That's another reason why it's not a red fiber. And as you can imagine, because it has scarce capillary supply, it does a lot of anaerobic respiration. Why would it do that? Well, you're not supplying it with a lot of oxygen to begin with, so it does a lot of anaerobic respiration. So how can I target these for bodybuilding? You do maximum or just sub-maximum exercises. Like if you can bench press 300 pounds, well then put 280 on there and bench press it 6 times. And you're using your fast twitch type 2B fibers. The rule of thumb back when I was in college and used to go to the gym was, and I don't even know if this is still the rule of thumb, by the way, but the rule of thumb was if you're doing it less than 10 times, you're using your fast twitch power fibers. If you're doing it over 10 times, then you're using your intermediate 2As and even sometimes your slow fibers. And they have another rule of thumb. If you can talk while you're doing it, then you're completely slow twitch fibers. Meaning if you can carry on a conversation without being out of breath. So that's just a couple of rules of thumb for you. Now let's look at the slow twitch fibers. They have small diameters. They have a long time to peak tension. As you know, they have a slow, okay, all this you know. Very high resistance to fatigue. In fact, hardly ever fatigue. They're red because they have high myoglobin and they have a lot of capillaries. That's 2 reasons why they're red. Look at this. Lots and lots of mitochondria. Another reason why they're red, by the way. Which means if they have a lot of mitochondria do aerobic respiration. These guys must be doing aerobic respiration, and indeed they are. So these are your marathon running fibers. And then we have these intermediate fibers, or 2A. And I'm not going to read down through all of these. You can see it. And by the way, I look at one thing. They're not red, but they're not white. They're pink. Why? They have a little bit of myoglobin, not none. You know, they have some mitochondria. They don't have dense capillaries, but they're not scarce either. So you can see why they're pink. All right. So those are the 3 types of muscle fibers. Each individual is born genetically with a genetically determined amount of slow and fast twitch fibers in their body. Most of us are about 50-50. Now, some of us are 70-30, 60-40, etc. Or 30-70, depending on which one you're talking about. So in other words, what I'm telling you is if you're born with 70% fast twitch fibers and 30% slow twitch fibers, then you're going to be predisposed to being good at power movements, like sprinting 100 meters, dunking a basketball, bench pressing 300 pounds, power movements. But you're going to be horrible at running 5 miles, and you'll probably never run a marathon. Well, I shouldn't say it that way, because what I'm about to say next is going to negate that. You're going to be predisposed to be better at running 100 yards, dunking a basketball, bench pressing 300 pounds. But does that mean you can't train for a marathon? Absolutely not. You can train for a marathon, and in fact, you can condition your slow twitch fibers to be a very good marathon runner. Now, 70-30 is a little, you know, you are tilted towards the power activities. Most of us are around 50-50. If you're 70-30, you're going to be really good at running, and you're going to find endurance activities probably irritating because you're not going to be naturally good at them. You're going to have to train up to them. On the flip side of that coin, if you have a lot of slow twitch fibers, you're going to be really good at endurance activities, but you're going to have a hard time generating the power needed for things like sprinting 100 meters in less than 10 seconds and dunking a basketball. But that doesn't mean you can't train up to it. The fast twitch fibers that you do have, you can build and condition and strengthen and get to that point where you can sprint 100 meters in 10 seconds. So if you know yourself and know what your what your predisposition is, what you are naturally good at, then you probably can figure out what your percentage of fibers are. Not absolute, but relative. You can say relatively, I have more slow than fast, or I have more fast than slow. But most of us are right around 50-50. All right, I'm really done with skeletal muscle at this point, but there's two other types of muscle I want to talk about. First is the cardiac muscle. Its contraction is identical to the skeletal muscle contraction. Identical to it, except for one thing. There are more neurons coming to it than just a neuron that secretes acetylcholine. Now, it certainly has the neuron that secretes acetylcholine as well. But the heart has neurons coming to it that secrete epinephrine and norepinephrine, and neurons coming to it that secrete acetylcholine. So there's lots of neurons coming to the different types of neurons coming to the cardiac muscle, not just the one flavor of motor neuron that we talked about with the skeletal muscles. In addition, there's another big difference, and that is this. In between cardiomyocytes are these intercalated discs. Well, actually, this is one here been cut, and this is one I colored through. I'll uncolor it. These intercalated discs, here's another one right here, are junctions between cardiomyocytes that contain gap junctions. And that means that the electrolyte changes in one cell can be passed on to another cell. And really, remember, all of that a depolarization wave really is electrolyte changes. So that means when one cell depolarizes, another cell depolarizes. And this, in fact, is part of what gives our heart its sinus rhythm. It's very these gap junctions within the intercalated discs are very important. Otherwise, the cardiac muscle is striated just like skeletal muscle, and its contraction is very similar. Now, smooth muscle. This is quite a bit different. Smooth muscle still has actin and myosin, but it is not arranged like it is in skeletal muscle. First of all, it's not arranged and lined up with a Z disc. They are connected to these dense bodies. So you can say, what are my contractile myofilaments connected to these dense bodies? All right. Smooth muscles can have gap junctions in between them, or they could be individual muscle cells that contract as individuals. And there's actually two names for these. One is a single unit smooth muscle, and that's when a lot of cells have gap junctions and they contract as a sheet or a single unit. And then there's multi-unit smooth muscles where the muscles are acting more independently. Sometimes a single unit are called unitary or visceral, by the way. So single unit and multi-unit smooth muscles are two different types. And we'll start talking about how smooth muscles contract. All right, here's a collage picture for you. First of all, let's look at the bottom first. I know you probably don't want to, but let's look at the bottom first. If you look at just the bottom picture, smooth muscles contract the same way a skeletal muscle does. A myosin head binds the myosin head binding site and swivels. Really similar. Okay, so what's different? How we get there. So let's talk about how we get there. The depolarization wave comes across the plasma membrane, and it opens voltage-gated calcium channels, and calcium rushes in. In addition, that depolarization wave opens calcium channels in the sarcoplasmic reticulum, and calcium rushes in. The bottom line is the cytoplasmic calcium skyrockets. That calcium binds a protein called calmodulin, and it looks like this when the calcium's bound to it. Calmodulin activates myosin light chain kinase, MLCK. So that stands for myosin light chain kinase. That's what calmodulin activates. It's the MLCK that phosphorylates the myosin head and makes it cock and able to bind to the myosin head binding sites. So MLCK does this right here. This is what MLCK is doing. But that MLCK couldn't do that unless calmodulin activated it. All right. So now that my myosin head is activated, phosphorylated and activated, now it can bind and swivel the actin. Now, huge difference coming up, and something very important. And by the way, this picture is not in your book, so you're going to have to pay attention to the lecture part of it. How do I relax? Cleave off those phosphates. So to relax, I have to cleave off those phosphates I just circled right there. A phosphatase enzyme does that. But here's the deal. I can detach and then cleave the phosphates so I don't reattach. Or I could cleave the phosphates while attached. But that's two different outcomes. If I detach and then do the phosphate hydrolysis, that is normal relaxation. However, if I do phosphate hydrolysis while attached, then I enter a latch state. And that's attached. But here's the deal. My myosin head stays attached, and it doesn't require any additional energy to stay attached and swiveled. I hydrolyzed the phosphates while the myosin heads were attached to the actin, and the actin stays attached and swiveled. And I call it the latch state. So think about this. Sphincter muscles are smooth muscles. So when they contract, they, like your iris sphincter muscle, constricts your pupil. Sphincter muscles going from your stomach to your intestine. Sphincter muscles around your capillary beds. If these enter the latch state, they stay contracted and they don't have to keep burning ATP to do it. So do smooth muscles have high endurance? Extremely high endurance. They can enter the latch state and not expend any more energy molecules. So that's the latch state of smooth muscle contraction. You have to hydrolyze the phosphates with phosphatase while attached, and you enter the latch state. If you detach first, if the myosin head detaches first, and then the phosphates hydrolyzed, then you get normal relaxation. So first of all, when the smooth muscle gets a signal, voltage-gated calcium channels open and calcium enters the SR. The calcium enters the sarcoplasm from extracellular and the SR. That calcium binds calmodulin and activates it. Calmodulin activates myosin light chain kinase. Myosin light chain kinase phosphorylates the myosin head and activates it. Now it's cocked and ready to bind. The activated myosin heads bind and swivel. All right. How do I stop this? Phosphatases. However, if the phosphatases cleave while attached, you enter the latch state. If the myosin head detaches and then the phosphatase cleaves, you get normal relaxation. All right, we already talked about multi-unit smooth muscles. That's when each smooth muscle cell itself acts as an individual, or it might not be just one, it might be 10, but the whole sheet of smooth muscle doesn't act like one. There's many units within that sheet. So you can think of it like this. One smooth muscle cell acts like an individual versus all the individuals interconnected and acting as one. The visceral smooth muscle is that second type. When all these individual smooth muscles are interconnected by gap junctions and they act as one, they actually all contract together. And that's how peristalsis of your intestines work. Different things like that. So that's why we call it visceral smooth muscle cells, by the way, because they're around your visceral organs and your abdominal pelvic cavity. And this compares skeletal, cardiac, and smooth muscle to you. That's what this compares. I'm just trying to see if there's anything I should point out. Yeah, you can see this big thing. What does calcium bind to in skeletal muscle? Troponin. What does calcium bind to in the cardiac muscle? Troponin. What does calcium bind to in smooth muscle? Calmodulin. So you can see that there. This is another chart for you from another book. It's good to look at other sources sometimes to see another viewpoint. So this gives you some skeletal, cardiac, and smooth muscle comparisons, starting from the organ level, all the way up from the organ level all the way down through. Okay, folks, that's it for the muscle system.